All right, so our next presenter, we have Dylan Weitzman here with Thor.
Hello, everyone. Oh, it's too loud, right? Oh, clicker. Perfect. Alrighty. Hello, everyone. I'm Dylan Weitzman, and this is Thor. We are a byproduct mining company for rare earth and uranium. We basically mine the waste of other mines. Pop quiz for everyone. What does a Tesla, a wind turbine, a laptop, and a Tomahawk cruise missile have in common? Anyone? Let's look at the supply chain and find out. They use electric motors, electric generators, they use hard drives, and they use missile guidance systems. And they all have in common is a rare earth magnet. And like the gentleman said, they use something called rare earth elements, these three specifically. So these metals are so critical to our energy infrastructure, our electronic industry, and our military defense, it's obvious we have a secure supply for them, right? Couldn't be further from the truth. Now, China controls 97% of the world's market for these rare earth elements, and the US manufacturing is over 88% reliant for them. And it's not just 3 elements that China controls, it's 17. They're used in over 440 industries in the US alone. They create over 600,000 jobs and over $328 billion in revenue a year. Everything from the camera we have right here, to the cell phone that you're on, to the TV that you watch Netflix on, even the car you came here with, the fuel you put in your car, and the medicine that you use, all use rare earth elements in their manufacturing. So if a company wanted to come into this industry and help diversify the supply, this $3.5 billion rare earth oxide market, it would cost them about $1 billion in 10 years to start up a rare earth mine. Literally a third of the market just to enter the market. And if this market by 2020 increases to $7 billion like it's predicted, it still costs a seventh of the market just to enter the market. So we've learned that mining rare earth elements as a primary revenue stream is no longer cost effective. Companies such as Molecorp or Avalon Advanced Metals went bankrupt or changed their business model entirely. We don't have a good electronic recycling industry in the US either. Processing rare earth, well, we actually process other countries' rare earth elements, not even our own. And byproduct mining. This is what China does to control the world's supply of rare earth elements. They get their rare earth elements from the waste streams of their iron ore industry. And Thor, it is our mission to get the rare earth elements from the waste streams of the phosphate industry. Every one of these black dots you see right here is an active phosphate mine around the world. There's over 400 phosphate mines and processing plants in over 53 different countries. But we get all of our rare earth elements right here in that red dot from China. But we can actually diversify the US supply right here in Central Florida, where Florida's phosphate industry, or better is known for, the fertilizer industry, produces about 20% of the world's fertilizer supply, 60% of the US fertilizer supply, and they also generate about 32 million tons of waste a year. That contains 500 tons of rare earth elements and over 600,000 pounds of uranium that we just stockpile in these giant mountains you see in the back, or we disperse in our fertilizer. So Thor has developed a nanofiltration system that we can actually integrate into a fertilizer company and start recovering these rare earth elements before they end up in the waste stream. So right here is where we can start integrating into the facility. And we've actually tested this out using product samples we got from Mosaic, which is one of the world's largest fertilizer companies. It took us about 8 months to get this phosphoric acid you see at top, and we're one of the only companies in 10 years to do so. We also have FIPER down here. They are the Florida Industrial Phosphate Research Institute. We got a lab from them, we got some small amount of funding, and we got a lot of equipment in order to test our material with. It took us over 6 months to do so, but we managed to make them a good strategic partner of ours. And through their combined effort, we were actually able to make a product that works. We can recover 52% of rare earth elements in uranium from the waste streams of Mosaic's filter, or Mosaic's phosphoric acid. So there's 3 types of technologies on the market right now that can potentially do this. We have solid phase extraction, which works just like your air filter at home, but it can selectively capture specific elements at an atomic level. We have ion exchange, which works by, well, exchanging one atom for another. We also have something called solvent extraction, which works just like how you have water and oil. As you shake it up, it separates again, but certain elements are captured in each of the phases that separate. So let's look at the cost considerations for each one of these. Let's look at the environmental considerations for each one of these. And let's look at which one of these actually work in, let's say, Mosaic's process. Looks like we found one that works, and that's the one that we're using. But we're not just winning alone here. We have made a lot of strategic partners along the way. For example, we are an affiliate of the Critical Materials Institute funded by the Department of Energy. Their goal is to diversify the rare earth supply here in the US and to make new technology that uses rare earth elements. We've also been working with Oak Ridge National Labs, the largest lab in the US. They're going to be doing third-party testing of our product to make sure that it works. We have Fiper, which I mentioned before. We're going through another grant with them. We have Salinas, which they're going to be signing a LOI for potential sales and distribution into other industries, such as the aluminum, iron, coal, and oil, because they too have rare earth elements in their waste streams. And Mosaic, the world's largest fertilizer company, is a strategic partner and potentially our first potential customer as well. They own over 8 mines here in Florida and Louisiana, and many more around the world. So meet the miners. We have Glenn Wagner. He's our CEO and R&D process engineer. He works with government contracts and customer discovery. We have Brandon Carpenter. He's our COO and nano manufacturer. He holds several patents. He's a Forbes 30 under 30 and a YC fellowship alumni. We have myself, Dylan Weitzman. I'm the CRO and separation technology specialist. I have worked on oil spill extraction technology before. Currently I've worked in the nanoscience lab for 2 years and I'm pursuing a degree in physics. We have Dr. Regis Stana. He's known as the godfather of uranium extraction for good reason. He pioneered extracting uranium from fertilizer. Dr. Melanie Beasy, she's an advisor of ours at UCF. She's an analytical chemist that has helped us understand the data we've been collecting. We also have Kevin Pope, George Grammatikis, Mark Blue, Terry Pierce, and Michael Judith. They've been helping us a lot with understanding the rare earth supply issue in each of their respective industries, business development, contracts, negotiations, and overall business growth and development. So right now we have the fertilizer industry and the rare earth industry. They run parallel to each other and there's no cross connection between them. These mining companies mine the ore and convert it into a fertilizer product that goes to their customers, and for every ton of fertilizer product they make 5 tons of waste that either gets stockpiled or ends up in massive mountains of phosphogypsum, it's called. And that right there creates a lot of liability and environmental damage. We have these US-based rare earth companies or manufacturers that use rare earth elements, and right now their entire supply chain is based on China's rare earth supply. This stifles the rare earth value chain. So what we're going to do is we're going to become the bridge between these industries. We're going to have a 5, 10, or 20-year contract with a US-based fertilizer company so we can start integrating into their system and extracting these rare earth elements and uranium from their waste stream. We can then start processing those rare earth elements through a third-party processor here in the US and starting to recover the valuable elements in each of their separate forms. We then have a 5, 10, or 20-year contract with a US-based company that needs rare earth elements to stabilize the supply, thus reducing China's reliance upon rare earth elements and also increasing the rare earth value chain. And the uranium that we have, we can start selling to the government or military applications. And for every ton of acid that we actually start filtering through, we can actually get 150 grams of rare earth elements from them. That right there is only worth $1.50. But through the processing, we can actually increase that value to $13 post-processing. So with the operational capacity of a plant, which is about 1.4 million tons a year of phosphoric acid they make, and the filter efficiency, which we have about 52%, we could potentially be getting about $8 million per plant per year. Now, as our filter efficiency increases, we can actually extract more rare earth elements, economics of scale comes into play, and our processing cost decreases. So we could potentially be getting $16 million per plant per year. Besides, Mosaic owns 8 of them. So right now we are working on finishing out the bench scale prototype that we have. This will allow us to understand more of the cost and engineering constraints that we're working with. We're also working on getting contracts and LOIs so we can start seeking investments for building the small scale pilot facility that we need. That right there would be about a $2.5 million to build a 1/100th scale of a product that we have. Then we can also start getting investments for either debt or equity financing for the commercial pilot plant that we want to build. That right there would cost us about $15 million, but the US government has something called a Metals Act. That right there is a no interest loan from the US government for a rare earth company. So once we have a commercial pilot plant and the contracts, we can start producing our nanofiltration systems that we can start integrating into facilities, and by 2022 we can have our first unit. So what have we done so far? We've had over 150 potential customer discovery. We have validated our market. We have built a strong advisory board, strategic partners. We have gotten a grant from the NSF through I-Corps. We have gotten samples from Mosaic, and we have a prototype that works. So next time you're driving by Lakeland and you see this giant mountain of radioactive fertilizer, ask yourself, is it a waste or is it a resource? Thank you.
So you went through ICOR. In that context, how do you define your customer segment? Who pays you money for what you sell?
The rare earth company that would need these rare earth elements, or the U.S. manufacturer that needs rare earth elements will be paying us for the rare earth elements that we're providing them. We have a contract with a fertilizer company. We would pay, like for example, we're looking at about a $5 million cost for a nanofilter to integrate into their facility. They get a 10% royalty of the rare earths that we sell as an incentive part. Considering that each plant we could potentially be getting about $8 million per plant, we'll be able to start recuperating those costs of each filter system in the first year or two.
All right, and again, in that context, what is the value proposition to your customer?
It reduces their waste and turns into a liability. No, it reduces their liability and turns into an asset because they're spending money just to stockpile this material. Now this material is actually making them money.
And what is the risk to them to working with you? What do you have to achieve before they'll be a customer?
We have to have a commercial pilot plant up and running for them to turn that LOI into a sale. We've talked with Mosaic, and that's what they want to see. They want to see a commercial pilot plant. Because this plant actually has to work for about 5, 10, or 20 years, because the average lifespan of a mine is about 30 years.
Thank you.
How many people from the team slide are full-time?
Us 3 are full-time. Dr. Regis helps us out a lot. Dr. Melanie Beasley, whenever we need help, she helps us out. And a lot of our other advisors, whenever we need assistance, they help us out.
Okay. And the processors aren't doing this themselves because of the technology and the patents that you have, is that correct?
We're finalizing our patents right now. We need a little bit more capital in order to do so.
Okay.
Two quick questions. On the slide that you had in there about where you're going to intersect yourself in the value chain, right? That kind of, yes, this slide. And just piggybacking on the question you just asked. So who is your customer?
Our customer are these individuals right here.
Right.
Their supply chain.
So not Mosaic.
They're the ones providing the waste for us.
Right. So they're your supplier.
Correct.
And so your contract, you're going to be generating revenue from Apple giving you a contract to supply them X amount of rare earth metals for 10 years.
Correct, because right now it's...
Or GE or BP or whoever.
Correct. A lot of these companies right now are all reliant upon China's rare earth supply.
No, understood. I asked that because I just wanted to clarify. It didn't sound like that was the same answer, towards it. All right, perfect. So just to clarify that. Go to the next slide in that timeline. How does that get sped up? 2017 to 2022 in your industry, it literally feels like it would be the Ice Age versus the Industrial Age, right? Why 5+ years to get production? How does that get sped up?
Through a lot of it's to do with capital and hiring the right individuals.
Right, so capital could speed it up. How much dollars, if you had tomorrow, could production be in 2019?
We're looking that would be probably $20 million to get to the production facility now. Yeah. Because the first part, the benchtop prototype, would take us about $250,000. The small scale pilot plant would be about $2.5 million.
Right. And
this one would be about $10 to $15 million.
Right. So plus less than 20 million, and you could do this a lot faster.
Correct.
Your timeline here is dependent on when you think you can get capital.
Once we have some collateral, we can actually go after the Metals Act, which is the no interest loan from the government.
Yeah, understood. I just don't think you have 5 years to get the first prototype done. There are a lot of people with $20 million that could do this a lot faster. So, but again, you've answered.
That's why we want to actually start getting contracts and LOIs for rare earth elements, so we can actually go to an investor and say, look, we have a contract with Apple for a 10-year period of time if we can deliver 500 tons a year.
Right. Absolutely, yeah.
Mm-hmm. So that's our next step right now.
Yep.
Who was sitting there and came up with the idea to take the waste from these kinds of mines and tricked other people into coming along and starting a company?
That was me. Driving by this one day, I asked myself, what is this? Florida doesn't have mountains, especially white ones. They have garbage dumps. So I was curious about what this was, and I started looking into it, and then we found out about FIPER and the Critical Materials Institute. We met Dr. Regis. He introduced us to Mosaic. He used to work at Mosaic for 15 years. We've met with the president and CRO of Mosaic, actually.
And how many people in the company today have equity?
Us three.
You three. And how did you split up the equity?
Right now it's a third each.
Okay. All right. And then was on the slide, there was a CEO?
Yes, Glenn.
Okay. All right. Oh, you don't look like your picture.
You got a haircut.
Yeah. Right. All right. And so how did he trick you into doing this?
One of the main problems that the U.S. faces in the military aspect is the fact that we don't have our own internal supply for rare earth elements and uranium. One of the things that the U.S. Navy is looking for is 15-year supplies of uranium from Spatewar Atlantic. They actually they view Thor as a high priority venture for potentially supplying future aircraft carriers down the line. We also use rare earth elements in a variety of satellites. Say, for example, you can use europium like we're getting in our second extraction process. That can be used to replace rwandium, which is a much harder rare earth element to come about.
But so how did you guys know each other?
We all worked, Brandon and I worked at the launch pad as well as the Nanoscience Technology Center. Glenn has the record appointments for the most times to launch pad, I think like 150 in a year.
No, it was like 150 in a year, and then it grew to about 267 total appointments. It was just going day in and day out.
We all came from the Blackstone launch pad at UCLA.
You came from what, sorry?
Blackstone launch pad at UCLA.
Okay. And then last question, tell me a little bit about what you guys did before.
Let's see, I worked on oil spill extraction technology before. Some of my old co-founders here, we started ventures before. I've been a coach at the Blackstone Launchpad for 3 years. Coached over 450 startups so far.
And then you guys?
I did some research work in the Department of Defense for like Office of Responsive Space. I also did ground-to-space weaponry, and Brandon can answer for himself.
So over the last several years, basically all I've done is nanofabrication, whether it be with ceramics, polymers, doing synthesis, characterization, and using them for a bunch of different applications, which is how I got wrapped up into this because I'm really good at building stuff at a nanoscale.
Thank you.
So you guys, let's assume you're not the only smart guys on Earth, okay? And
although give me these first 2 rows, it might be.
Yeah, that's right. Other than us, right? So I get the issue with China, but fundamentally, I suspect most of that market doesn't care where it comes from. Maybe the military has some particular interest, but if it's as big a deal as you make it, and this country being as creative, probably the most creative country in the world, why has anybody done something like this before?
Other companies and other industries doing this. For example, a bunch of companies in West Virginia are trying to extract rare earth elements from the coal. A lot of companies are trying to go after the iron ore industry. We're going after the phosphate industry.
Right. No, I get it. You're going after it, and these other guys are going after it too. But if it was that, if the market is as big as you say it is, and it's possibly as lucrative as you say it is, and it doesn't, it's the amount of upfront investment to get this to a point where, can I do this or not? That's probably the scariest piece of what you're presenting today. And I know you have prototypes that think you can get there, but there's a lot of money invested, and you're looking at 50 or 75 million bucks, and it's probably 275 million, and we'll still find out how much more it is. Those kinds of things just happen in all of these kinds of projects. The concern I have is why, if it's that big a deal, why nobody else is really doing what you're doing and satisfying the Apples and the IBMs and that world. And then what keeps Mosaic, since you don't really have any intellectual property today, what keeps Mosaic from watching you guys do this and then saying, all right, it's ours? I mean, so they can buy something from you, I guess. But the whole thing just, it's a story that's got, from a venture world, it's got a lot of holes in it. And it needs an awful lot of money to get where you want to be, and it's just hard to get there. So I guess what I'm looking for is, can you give me something that says this market is real, we are there? I mean, you say you can be there, but there's no real proof of it. And why is it just nobody else is trying to do this?
There are other companies trying to do it in different industries. We're one of the few companies that are doing it in this industry, in this specific part of Mosaic system. There's a few companies that are going downstream of Mosaic, but the conditions are not as harsh, and there's not a lot of rare earth elements in there. A lot of companies go after small quantities of rare earth elements that are a little more viable. We're going after something that's going to be longer-term supply, a little more risk, of course. But a lot of the things that we're doing is we're building strategic partners. We're getting people that can really help us out, such as Oak Ridge National Labs. One of their main focuses for research is rare earth and uranium extraction from phosphoric acid. We're working with that team.
So let me ask you a quick question. So the customers that are down below, can you characterize their buying patterns for rare earth elements? Meaning, and I'll give you an example. Those of us in the industry know exactly how Apple buys PMICs, right? Power management integrated circuits. We know exactly how they buy them, who they buy them from, how they qualify them, how they put them into their devices, how they use them, how they transition from generation. Are they or other folks in there actually buying the rare earth materials and processing them or putting them, or is it through an ODM channel, or is it a component to one of their components?
That's why we want to go.
Can you get the mic back?
Right.
No, right there.
Oh, we have one. Yeah, what we want to do is we want to start with companies such as Apple, Tesla, SpaceX, DuPont, and track back through their supply chain by talking to their chief supply officer to find out where specifically in their supply chain is this issue occurring.
Right, because I can tell you where it is in Apple. It's not close to Apple. So Apple doesn't spend time worrying about rare earth elements or where they're coming from. They're focused on components and component performance, and so there's someone way earlier in the chain that has these rare earth elements integrated into their fundamental components. So the notion that that Apple is going to somehow use this as a, for lack of a better term, a hedge to the price or access to rare earth, it's so far down in their buying chain, right? And I can't tell you that for companies like Tesla, who are probably winding their own motors, or GE, who are using it in parts of their turbines and those types of things. But for the consumer electronics guys, there's not someone who has a little line for rare earth elements on the build, for procurement or build on those things. So what I'm trying to figure out is who is actually accessing that commodity product and then putting it into an underlying piece of electronics. Yeah.
One of the things we're doing through the National I-Corps program that we're entering into is to find out these specific customers through a lot of the customer discovery. Starting with, for example, Apple will talk to their supply chain officer that will lead us down the line for them. That's what we want to be start doing right now, because if we can get that contract or an LOI from that specific individual, we can now take that to an investor and hopefully start getting funding to build out our prototypes or commercial pilot plant. So we know that we have some work going back to the supply chain.
As far as funding, you had a $2.5 million cost for the small scale plant. $250,000 was for what?
That's the lab scale. That's for a small little tabletop version that we can fit in on a lab table that works on a continuous 24-hour process.
So what's the next thing that you're looking to fund? Is it that?
If we could get funding for that, right now we're applying through grants in order to fund that aspect. A lot of the larger capital requirements are the small scale prototype, which would be 1/100th of a scale of the commercial pilot plant. That right there would tell us a lot of the engineering design costs that we need to consider.
And that's after the lab scale?
Correct.
How much is that?
That would be $2.5 million.
Oh, that's the 2.5. Okay.
And why does that have to be built versus some fancy software that could tell you what?
A lot of it is.
The question was simulation. Can you simulate?
We were thinking about using a simulation software like COMSOL Multiphysics, but that would just take too much time and effort to find the expertise that have chemical manufacturing knowledge in that specific area. Right now, we know individuals at Oak Ridge that could help us with building this out through a sub-awarding, through a grant.
A lot of this we can do through modeling and simulation. However, a lot of the research we've already done, even at its current efficiency of 52%, we could actually take it to market as is and still be economically viable. So most of the testing we're doing now is just proving that it has the durability to last in these conditions over a period of time. And while we could simulate it, at this point we're far enough along to where, in all honesty, it'd actually be a better use of our time and resources to do it experimentally. It'd actually end up being faster for us to do it like that rather than to simulate it and then do it. But we could do the simulations if we wanted.
Yeah, we actually went from 30% efficiency during the first few rounds of the prototype up to almost 60 like we see right here. with a very high affinity for europium, which in your slide decks I have for you, you can actually see that right there is the most critical element the government needs yesterday, is europium.